Hey everybody, welcome to lesson number 5, which is on Le Chatelier's principle. Everything that you guys have done so far in equilibrium has looked at it from a quantitative perspective, so calculations and numbers. But there is a qualitative perspective called Le Chatelier's principle, or we use Le Chatelier's principle to determine that qualitative analysis of what we're looking at. And in order to facilitate this, we can always ask ourselves, what happens to a system that's at equilibrium if one of the chemicals changes, or if some of the conditions under which this reaction is taking place changes? Much of industry relies on a knowledge of Le Chatelier's principle to help create products for consumers. So in order to facilitate this, industry may, for example, add more reactants to make more of their product, or they may pull product out so that the reaction continues to make product, or they may heat it up, or they might change the pressure, or they might do a whole bunch of different things. When this is done continually, you're going to make more of your product, which is ultimately the name of the game. You want to make as much product of whatever it is that you're trying to create so that you can sell more and more and more of this product. So last day, you guys looked at the Haber process, which took atmospheric nitrogen and reacted it with some hydrogen, as shown in this equation here, to produce ammonia. So imagine now I'm a producer of ammonia. I have a business and I am a producer of ammonia. Of course, I want to produce as much ammonia as possible. So when we performed our calculations last day, we discovered that under the conditions that were set out by that question and calculated that the reaction would push left. Now, if I'm a producer, that's not good for me. I don't want it to push left because I don't want to make N2NH2. I want to make more ammonia. And so is there a way that we can make our reaction quotient cause the equation to switch sides, push to the right to create more ammonia? And the answer is yeah, we can. We can pull out more product. And if I'm pulling out more product, then I'm decreasing the size of my numerator in my reaction quotient expression. You guys will be reminded from last day. And if I'm decreasing the size of the numerator, it's causing my Q value to go down, which is what we want. And we want it to go so low that it's actually below the 0.4 that was outlined in the question from last class, so that we start pushing our equilibrium to the right. Or perhaps we can do it in another way. Perhaps we can add N2NH2. If we add N2NH2, then I'm going to increase the size of my denominator, which will also shrink my Q value. And if I'm increasing my Q, or if I'm decreasing my Q value, it's going to get to a point where the reaction will flip and I'm going to be producing more NH3. So you can see how we can manipulate these equations to get the results that we want. Now, if we're looking at the actual definition of Le Chatelier's principle, Le Chatelier's principle says a dynamic equilibrium tends to respond so as to relieve the effect of any change in a condition that affects the equilibrium. Oh my God, that's very much chemistry babble. Let's just talk about it in general. It just means that whatever stress I put on the system, whether it's to add something or take something away or whatever that stress might be, the system is always going to try and counteract that stress. So if I pull products out, it's going to try and make product. If I pull reactants out, it's going to try and make reactants. If I change the pressure, well, it can go in either direction. We're going to talk a little bit about that a little bit later. But you guys get the idea that this is a qualitative method that is rooted in understanding how the reaction quotient and equilibrium mass action expressions actually work. So I'm not going to spend too much time on common ion here. And the reason I'm not going to spend a lot of time on this is we have a full lesson on common ion coming up. It's a little bit later on in the unit. Actually, it's like 3 or 4 lessons ahead of us. We're 3 lessons from now. But in any case, I'm not going to spend a lot of time. But basically, the common ion effect is an effect on equilibrium based on the concentration of like ions in solution. So for example, let's say I had a solution of sodium fluoride and I wanted to dissolve sodium chloride into the solution. I would certainly, it will dissolve, but it will dissolve to a lesser amount than if I was dissolving it in pure H2O because of the presence of the sodium ion. That sodium ion, where it's in solution already, is going to force the second equilibrium to the left. It's going to cause that sodium chloride to remain in solid state because I already have sodium in solution from the sodium fluoride there. Beyond that, I'm not going to get into that right now. We are going to talk about the common ion effect a little bit later. Don't want to stress too much about that. But we are going to talk a little bit more in detail about temperature and equilibrium, and then pressure and equilibrium. So the value of the equilibrium constant changes with temperature. And you should know that because the equilibrium constant is the ratio between the forward and reverse K values from our reaction rates. You guys know that those K values change with temperature, and so the equilibrium constant will change with temperature. And as a result of this, we can actually look at energy terms for chemical reactions and place them into our chemical reactions as if they were reactants or products. So let's take a look at this example. I've got two SO3s, and it's going to produce two SO2s and an O2. And you'll notice that the delta H for the reaction is 197 kilojoules. It's a positive value, which tells us that it's an endothermic reaction. Now, in when we did the second unit and we looked at energy and rates, I showed you guys multiple ways on how you could represent thermochemical equations. And one of the ways that I showed you is actually having the energy term in the equation. I would highly suggest that for the equilibrium unit, when you are dealing with energy term thermochemical equations, that you make sure that you have in your equation your value. So it's an endothermic, so it goes on the reactant side. So you'll notice that I have it here. If I were to add heat to this particular reaction here, it's as if I'm adding the heat term, the energy term, to the reactants. And so the system is going to try and counteract that. And so it's going to push away from that stress. So if I'm adding heat, it's going to push to the right. And the reason is because it's the same thing as adding like SO3. It's the same thing as adding a reactant. It's going to push to make more products or to decrease the number of reactants that I have created. If I were to take away heat, that's as if I'm taking away a reactant, then my equilibrium is going to try and make reactants. It's going to push to the left. So it's always going to do the opposite of what you're doing. So if I've got heat here and I add heat, it's going to push to the right. Because if I'm adding a reactant, it's going to push to make products. It's going to try and decrease the amount of reactant that I'm making or that I've added to the system. Okay, so that's how heat works. So make sure that you guys have your heat term, or you just put an E if you don't know the actual value, and I'll give you an example of this a little bit later. But always put that E value where it is in the thermochemical equation, and then treat it as a reactant or a product. And I'm going to give you guys an example coming up. Pressure is a little bit more complicated to understand. So before we actually start talking about pressure, you have to understand what pressure is. Pressure is a force per unit area. In other words, it's the amount of force that the gas particles, because this is always created with gases, it's the amount of force that those gas particles are exerting on the surface of a container. So for example, if I have a balloon, that particular balloon stays upright in its blown up position because inside the balloon there are particles that are striking the inside surfaces holding that balloon up. And so that's what we have when we're talking about pressure. Now, how can we increase that pressure? How can we decrease pressure? Well, if I add more particles into the balloon, I can increase the pressure. And that makes sense because now I've got more particles striking the inside of the container. And so if I'm pushing outwards with more hits, it's going to increase the pressure. If I decrease, it's going to do the reverse to that. What happens if I change the size of the container? Let's say I make my container smaller. So let's say I take a balloon and I start squishing the balloon down. You'll notice that as you squish that balloon down, you're starting to feel pressure pushing your hands outwards. It's trying to push your hands away. Well, why is it doing that? Well, because now, as I shrink that balloon down, the amount of surface area inside decreases, but the number of particles remain constant. So now I have more particles striking a smaller area, my pressure is going to go up. And the reverse is also true. If I make my container bigger, it's going to make, without changing the number of particles, it's going to make my pressure go down. So let's think about this with respect to Le Châtelier's principle. Remember, Le Châtelier's principle tries to counteract the stresses that I apply to it. So let's say I increase the amount of force that on the outside of the container. I'm shrinking the container down. Well, how is my equilibrium going to shift? Well, my equilibrium is going to shift to try and decrease the pressure. So if I'm increasing the pressure, it's going to try and decrease the pressure. Well, let's take a look at this particular equation, same one from above. So it says two SO3 gases turn to two SO2 gases and an O2. If you notice on the left side of this equation, I only have two particles. I have two SO3s. And on the right side of my equation, I have three particles. I've got two SO2s and an O2. And as a result of me having three particles on one side and two particles on the other, if I increase pressure, the system is going to try and decrease the pressure. So it's going to push to the side that has fewer number of particles. So let's say I increase the pressure, which way is it going to go? Well, if I increase the pressure, it's going to want to push left, because to the left I have fewer particles, and as a result of me having fewer particles, I'm able to decrease the pressure. If I did the reverse, if I expanded the container that it's in, it's going to push to the right to try and increase the pressure so that the equilibrium constant remains there. Now there is a lesson, and you guys can, basically what I said is just written here in paragraph form, but there is actually a lesson on Kp, which is the equilibrium constant with pressures. Have a read through that lesson. I'm not going to do a formal lesson on it because I know a lot of the other teachers don't cover it. But have a read through it, and when you look at the equation itself, you'll see why there is a change in pressure or change in number of particles as we change pressure, and what would happen if you had the same number of particles on either side. So let's add two particles and two particles. Changing the pressure would have no effect then on the equilibrium there. But let's talk about some examples here. So I did talk about this example. That's easy enough to understand, but you can relate this to something. So think about that water bottle that we talked about that you left in your car overnight, or perhaps the balloon that you leave in your car overnight and it's cold. Well, what happens to that water bottle? Well, the first thing you'll notice when you go in the morning is that the water bottle has depressed down, like it's scrunched down. Well, why is that the case? Well, at nighttime, the temperature dropped, so you had condensation of the water vapor in the air part of the water bottle into its liquid form. Well, if I'm losing particles of gas to the liquid form, my pressure is going to go down. And if my pressure is going to go down, then the only way to counteract this whole system is by decreasing the size of the container so that it maintains that same concentration of gas particles. So that's a good example of this. What about temperature and equilibrium? Well, here I have an equation. This equation is really interesting. Most of you guys probably use this equation every day, but you don't realize you're using it. This chemical here, C8H18, is octane. It's what we put in our cars. And you guys know that our cars are internal combustion engines. So if I take C8H18 and I burn it in oxygen, I produce carbon dioxide, water, and I produce energy. Well, think about what would happen to your car if it started to overheat. The first thing that you would notice when the car overheats is that it stalls, it shuts off. Well, why is it shutting off? Well, the only way that the car is going to shut off is if the reaction that's happening inside the car is no longer able to happen. If I add heat, I'm adding here. So the only way to counteract that process by adding heat is to push my equilibrium left. So remember, the E term is on the reactant or the product side. And so if it's on the product side, we consider it to be a product. And so as a result, if I add heat into the system, the equilibrium will push left. And if I'm pushing left, no more combustion happens, shut your car off. So that's exactly a good example of temperature and how temperature can affect equilibrium and chemical reactions. So I hope you guys understood this. Do the practice that's in the packages. Email me if you guys have any questions and we'll go from there. Thanks guys. Have a great one.